Greetings to all and welcome to this lecture. We are in module 4, lecture number 4. So, let us do a general analysis of our 3-terminal MOS structure, what we have discussed in last lecture. We have discussed that how the introduction of third terminal is contacting the inversion layer. So, in 2-terminal structure we said that the inversion charge are only coming from the body. However, we said that if we introduce another terminal which is C, then how this C to B voltage, means this contact to body voltage is affecting my surface charge as well as surface potential. So, this is QC dash, here you have an oxide and here you have metal, where you are actually applying VGB. So, this is gate terminal and this potential is, you call it as surface potential. So, in this lecture let us form a general analysis as we have already done in 2-terminal structure. These are the learning outcomes of this lecture, which helps us to frame out the general analysis of charge and potential equations. Let us do a quick recap. So, we said that in 2-terminal structure we have gate and we have body. When we connect a gate to body voltage, this causes some amount of surface potential, and this surface potential is actually causes a surface charge. For the sake of simplicity, we said that let us consider VGB is equals to V flat band voltage, meaning there is no charge present into the surface. So, QC dash is equals to 0 and psi s is equals to 0. At that moment we said that let us introduce another terminal which is contact and connect a voltage between this. We started our analysis with the baseline understanding that what will happen if this contact and body will be shorted. Even if we short, that this N plus P junction can have a built-in potential, because this depletion region is expanded in the P body. So, this is P type semiconductor and the depletion region expanded in this region, and there is a depletion region expansion at the N plus region also, which we ignored for the simplicity. What we said is this built-in potential between N plus and P, which was given by phi b I, is same as this built-in potential, because we considered that the VGB is V flat band voltage, and hence the potential at the surface is exactly equals to the body. So, this is nothing but phi b I. We drew the conduction band energy and said that because of this built-in potential there will be a potential barrier exist, which is Q times of phi b I, because we are again plotting energy in y axis. So, this is in electron volt, we need to multiply by Q. The electrons are distributed here in N plus region. The lower energy levels are highly probable and the upper energy levels are likely less probable to filled with electrons, and the carrier density which crosses this junction is actually varies with the barrier height. Then we said that can we reduce this barrier? So, the answer was yes. By applying the VGB we can increase the surface potential here, and the moment when we increase VGB, the increased surface potential by amount, let us say Q into psi 1, reduces the barrier height from this A to B. If the barrier height got reduced, so the effective reduction in the barrier is what? Q times of phi b I minus psi 1, which means you are making the junction as forward bias, because you are applying a positive voltage at the P side. This increases the attractiveness of the electron to move from N plus region to surface, and hence the inversion forms. So, here the inversion electrons will come into picture. Then we said that what will happen if VCB is non-zero, meaning we are applying some voltage of VCB. If VCB is greater than 0, now the system goes in non-equilibrium state. meaning this VCB causes a Fermi level shift into this n plus region, which is considered as quasi Fermi level. We also plotted the band diagram stating that how this VCB shifted the quasi Fermi level. Now let us understand first this band diagram. By applying the VCB, the energy barrier will again get lowered at this end, and hence the electrons which were available at the surface got the reverse attraction force towards the n plus, and hence if you increase VCB, there might be a chance that the possibility of this inversion layer will gone, meaning there is a chance that the inversion layer will disappear. So we need to increase the same amount of conduction or the same amount of charge in the surface, we required more amount of VGB. So by applying more amount of VGB, we need to increase the surface potential in such a way that the barrier height will goes to the actual barrier height. So this can be attained by increasing VGB in such a way that the surface potential will be now psi s plus times of psi s plus VCB. So we argued on that in two terminal MOS my surface potential was fighting against 2 phi f to get into inversion from depletion, whereas in 3 terminal MOS the surface potential is fighting against 2 phi f plus VCB. Here the VCB role comes into picture. We also argued that if we really want to use the previous equations what is derived for 2 terminal structure can be used only by replacing n naught by n naught into e to the power of minus VCB by phi t, or psi s is equals to 2 phi f can be rewritten as 2 phi f plus VCB. So if you see, the VCB is actually introducing in the structure by n naught into e to the power of minus VCB by phi t term, which means the VCB term is only affecting the inversion charge, meaning the electron layer which is present into the surface. It is not affecting the depletion and accumulation. That is what we are going to see. Let us do a general analysis what we have already done for 2 terminal, but here we need to take care that we are applying a VCB voltage from the 3rd terminal. So I am redrawing this 3 terminal structure as n plus, this is your gate body and this is your VCB. By analyzing the band diagrams and the surface charge equation, we said that this surface potential is actually influenced by this VCB, and hence the attractiveness of this surface is actually defined as whatever be the total potential developed between this surface and bulk minus VCB. It means it is not like how much surface potential do you have to attract the electron. Instead you can say how much surface potential you have over VCB value. So you need to take psi y minus VCB. So if I want to write a junction law again to find out the total electron concentration near the surface, and this is again y direction, this is x direction. So ny can be written as n naught e to the power of psi y minus of VCB divided by phi t. If you remember, we have done the general analysis for the electron concentration in 2 terminal structure, where we said that this is surface potential, or this is the potential which is responsible for the electron to come at the surface, and at that moment we wrote ny can be given as e to the power psi y by phi t into n naught, which gives that the electron concentration here will be higher as compared to the bulk concentration. So here n naught is equilibrium carrier concentration of electrons and P naught is an equilibrium hole concentration for p type body. So obviously when you apply a positive voltage, this positive voltage of psi y dropped here will causes more number of electron, and hence you are getting a positive exponent. Likewise, we have also derived the whole contribution. right, or the hole concentration. The hole concentration can be given by P naught e to the power of minus psi y by phi t. Again, the P naught is higher in p type body, but when you apply a positive voltage, the hole will get repelled back to the body, and hence at the surface or along this y, what will happen? The hole concentration will reduce, then its equilibrium value. That is what the minus exponential is coming into picture. It is interestingly note here that VCB is only altering the inversion charge, meaning the VCB is actually affecting the electron concentration. That is what we have already discussed in the previous lecture, that if we really want to introduce the VCB impact, we need to replace N naught by N naught into e to the power of minus VCB divided by phi t. That is what we are doing here. But the hole concentration will not get affected. The hole concentration remains same, because you are applying a reverse bias here, and there is no attraction force of those holes towards this N plus region. So, you have electron concentration, you have hole concentration for general y, right, for general potential which is psi y. Can I write the total charge density? So, the total charge density can be written as hole contribution, which is nothing but P naught e to the power of minus psi y by phi t, electron contribution, which is minus of N naught. Here N naught can be replaced by N naught into e to the power of minus VCB divided by phi t into e to the power of psi y by phi t, right. So, let me erase this, plus the donor concentration and d minus the acceptor concentration. If you recall that we have done this kind of analysis for two terminal structure, where we said that the total charges available into the surface is due to holes, due to electrons, and due to immobile ions, correct. Then we said that we can relate this charge density, which is a function of y, to calculate the total potential. What is the potential developed at the surface with respect to deep in body? So, we wrote the Poisson equation, which is nothing but delta square of psi by delta y square is equals to minus of rho y divided by epsilon s. So, if you rewrite this equation, you will get this equation, which relates the potential and the charge. Now, how can we proceed to solve this equation? Again, to solve this equation, you multiply by 2 times of d psi by dy at both sides and integrate considering a dummy variable y. If you multiply this at the left hand side, dy square, so I am not writing this, it is same as this multiplied with 2 times of d psi by dy. The left hand side is nothing but d psi by dy whole square with d by dy, and when you integrate it, the left hand side will give you the electric field square, it means d psi by dy whole square, and the right hand side also you can solve considering a dummy variable y dash. When you do the integration, you will get a equation related to P naught e to the power of minus psi y by phi t minus N naught e to the power of minus VCB divided by phi t into e to the power of psi y by phi t plus N d minus N a, and now you need to integrate this part between a proper limit. This is d psi by d psi. So, the limit we have already decided that it will be 0 deep in the bulk and it will be psi s at the surface potential. So, we did this kind of all analysis to find out a closed form equation of channel charge. If you do this kind of in this integration, then the total equation of channel charge can be given by this, which simply says that the total channel charge having a contribution of hole, dopants and electron. and then we use this equation separately to find out the individual impact in accumulation, depletion, weak inversion, strong inversion, and so forth, right. So, we will derive this equation for 3-terminal MOS structure as well, where interestingly it is to be noted that the VCB term, which is the contact to body terminal voltage, is only introduced by the electron contribution. There is no VCB term in the hole contribution and the immobile ion contribution. So, we said that the inversion layer which is available near the surface can be controlled by VCB, and hence you need to replace this N naught by N naught into minus of VCB. We can use this expression to simplify by considering again the boundary condition. We considered the boundary condition as in flatband voltage the surface potential is 0, and at that moment you can find the charge neutrality equation, which says that minus of N naught plus P naught plus Nd minus Na is equals to 0. If you replace P naught minus N naught is equals to Na minus Nd, then the complete equation can be written in terms of this, where we have taken Na, which is nothing but P naught considering all the dopants are ionized, and for p type semiconductor we can simply write P naught is nothing but Na. So, you take Na outside, you will get the same expression what we have derived for 2-terminal MOS, and this equation holds good for all region of operation, whether your structure is in accumulation, depletion, inversion, strong inversion, and so forth. So, ultimately you see that VCB term is coming here. That is what we have discussed in previous lecture, that either you replace N naught by N naught into e to the power of minus VCB divided by phi t wherever you find N naught, and you can use the same equation what we have derived for 2-terminal MOS, or you replace psi s is equals to 2 phi f plus VCB, or wherever you have used psi s is equals to 2 phi f, you need to replace psi s is equals to 2 phi f plus VCB, meaning your surface potential is not only fighting against 2 phi f to attain this kind of inversion, depletion, or so specifically inversion, then rather psi s is actually fighting with 2 phi f plus VCB. Let us see few more equations related to the 3-terminal MOS structure, that these equations what we have written as potential balance and charge balance equation holds good even for 3-terminal structure, because for the simplicity we said that the 3-terminal structure, this junction is very away from this side of the gate, and hence we considered that the length of the gate is very much high, so that the corner effects is not introduced, right. In that condition, if we write a potential balance equation in terms of VGB, then this will be same as 2-terminal structure. So, if you apply VGB, this VGB will drop across the oxide. So, let us consider this is your oxide, and it will drop across your surface. So, the potential balance equation will be same as VGB equals to psi ox plus psi s plus phi ms, where phi ms is the contact potential. Similarly, your charge balance equation holds good even for 3-terminal structure, which says that Qg dash plus Q naught dash plus Qc dash is equals to 0, where Qg dash is gate charge, Q naught dash is oxide fixed charge, and Qc dash is channel charge. Interesting to note here is the Qc dash, which was a channel charge, earlier in 2-terminal it was the function of only gate to body voltage, but now your inversion charge, which is a part of channel charge, is controlled by VCB also, and hence you need to write that Qc dash is now become a function of psi s, which is nothing but a function of VGB and VCB. So, like your VCB, the extra third terminal voltage is introduced by the electrons in your two terminal structure. So, all the equation holds good, and if you plot the QC dash versus psi s, you will get the same kind of curve, only the taking away point, meaning the point where the inversion charge just shoot up because of exponential dependency is get shifted, which makes sense that earlier what you said is when the surface potential is become positive, you are in depletion, and till phi f it is in depletion. After phi f you were in weak inversion, and beyond to phi f you were in strong inversion. But now when you applied VCB, the surface potential is reduced, and hence the attractiveness of your surface is got reduced. To increase the attractiveness with the same level of inversion, you required more voltage, more VGB, and that is can be given by that surface potential. It should be equal to 2 phi f plus VCB. It means now your surface potential will fight against 2 phi f plus what amount of VCB you have applied. So, this curve is same as two terminal structure, though the scale will be different, but this is when VCB is equals to 0. So, this curve is similar as two terminal structure, but when you applied VCB, which says that the shifting of or getting the inversion at the surface will be delayed. You see, this curve or the flattened part of the curve is not get affected, because this flattened part is nothing but the depletion part, which we called it as QC dash is equals to square root of 2 into Q into Na into epsilon s into root psi s. So, this curve shows a depletion curve, and hence VCB is not affecting your depletion, rather it is not affecting, and it is not affecting your accumulation also. So, VCB impact is only visible when you are talking about the inversion or the electrons present at the surface. Let us see the impact of VCB in other parameters like capacitance and the effective gate voltage. As we have discussed already, it is not of interest that how my QC dash varies with surface potential, rather I need to see how my QC dash or psi s varied with gate to body voltage, because the gate to body voltage is an independent variable which you are applying externally, and you need to see for what amount of VGB, what amount of surface potential is coming up, and for what amount of surface potential what is the gate charge, correct. So, we need to rewrite this potential balance equation, which simply says that VGB is equals to phi ms plus psi s plus psi aux, where psi aux can be replaced in terms of gate charge as phi ms plus psi s plus Qg dash by C aux dash. Here the change in the gate charge is can be replaced by the change in the oxide and the change in the channel charge. So, phi ms plus psi s, and this Qg dash can be written as Q naught dash by Cox dash minus Qc dash by Cox dash. This quantity is flat band voltage, and hence ultimately you will get this equation which says that VGB is equals to V flat band voltage plus psi s minus Qc dash divided by Cox dash. Just now we have derived the closed form equation of Qc dash for 3 terminal MOS, including VCB in our term as a whole contribution term, or the VCB term as which is influence the whole contribution. So, you can rewrite this equation in a closed form which says that how my surface potential is related with the gate to body voltage, where this gamma is already defined parameter which is called body effect coefficient. So, gamma is nothing but square root of 2 into Q into N into epsilon s divided by Cox dash, where Cox dash is nothing but epsilon Ox divided by Tox. This is the effective permittivity of oxide, correct. We have also proposed a simplified version of gamma by considering all these known parameters, and we said that gamma is can be given by this. Let us further see the impact of the VCB in gate charge. Again, if we derive all those equations of the gate charge considering VCB as constant, then we will get to know that we will get the overall Cg dash is can be given by a series combination of Cox and the channel capacitance Cc dash. Here we are not saying Cgb, here we are saying Cg dash, because now you are actually calculating the overall capacitance of 3-terminal structure. It is not the capacitance measured between only gate to body, right. So, overall capacitance, effective capacitance can be given as 1 over Cg dash is equals to 1 over Cox plus 1 over Cc dash. Here Cc dash is again can be splitted as what? Ci dash plus Cb dash, and we know that Ci dash and Cb dash can be rewritten as delta of Qc Qi dash by delta of psi s. This is the charge equation which actually includes VCB, and hence if we do the same kind of integration what we have proposed in 2-terminal structure, you will get a closed form equation of Cc dash, right, where if you closely see this term in the 2-terminal MOS is only minus of 2 times of phi f, but here you need to replace 2 phi f plus VCB, what we have already discussed in few times. So, this is can be replaced by 2 phi f plus VCB. Similarly, here this 2 phi f is replaced by 2 phi f plus VCB, and this is nothing but electron contribution. We have already discussed this part, that this equation is giving 0 by 0 form for psi s is equals to 0, which does not mean that the capacitance does not exist in flat band condition. We said that in the flat band condition, though the charges are not available into the surface, but the change in the charge is there, and the capacitance can be defined as the change in charge. So, we used L'Hopital's rule to calculate the capacitance in flat band condition. This holds good, and if you see, you are getting the same kind of expression for psi s is equals to 0. It means again at psi s is equals to 0, you do not have electron concentration in the surface, and hence VCB term will not come. Again, as we have already discussed, that VCB is actually affecting your inversion charge, and hence it is not affecting your accumulation and depletion. So, if we see the overall equation of charge in accumulation, it can be given by square root of 2 into q into Na into epsilon s into e to the power of minus psi s by 2 times of phi t. This equation says that my total channel charge is given by the whole contribution, which is exponential dependence with respect to psi s. So, if this is psi s, this is your Qc dash, and this is not get affected by VCB. Similarly, the depletion charge Qb dash is can be given by negative of 2 into q into Na into epsilon s into square root of psi s. In this equation also the VCB is not coming, and hence we can simply say that VCB is not affecting your depletion charge also. That is what we have already seen in the previous graph, where we said that this point was phi f, 2 phi f, and this point was 2 phi f plus VCB. During this transition from 2 phi f to 2 phi f plus VCB, this slopes remain same. It is almost same in depletion. We agree that the shift, there is a shift in the surface potential value in depletion, but the charge is not changed, charge is not affected by VCB value. So, let me summarize. In this lecture, we have thoroughly analyzed the 3-terminal MOS structure in terms of channel charge, surface potential, and applied gate to body voltage. We have seen that all the equation holds good for 3-terminal MOS, which we have derived earlier in 2-terminal MOS. The only difference is you need to replace N naught by n naught into e to the power of minus VCB divided by phi t, which says that VCB actually influences your concentration of electrons at the surface. Instead, you can also replace 2 phi f by 2 phi f plus VCB when you are talking about strong inversion case. We have also seen that the capacitance and the surface potential is all get affected by VCB when you are talking that electron is coming into the picture, or you are talking about the strong inversion case. The VCB factor is not influencing your accumulation and depletion, because in accumulation the hole is majority and in depletion the immobile ions are majority, which is not get influenced by VCB or from the n plus p junction built-in potential. So, we will stop here for today. Until then, take care.